Thanks to everyone for joining the session. So over to Mathilde Gerbelli-Gauthier for her second talk on cohomological representations.
Thank you very much, Professor Khandai. Thank you for the invitation. Thank you for the introduction. Thank you for attending the talk. So this is a follow-up talk, or sort of second part of the talk I gave 2 days ago on cohomological representations. And again, it's concerned really with the sort of the spectral decomposition of the cohomology of arithmetic groups. And I think we're leading on to sort of some, in this series of talks, some more recent work about the cohomology of arithmetic groups. And so today, on Tuesday, I gave some sort of general outline of how cohomological representations are characterized, classified, etc. And today I thought I'd really do everything in pretty explicitly for the group SP4. So the reason why I chose SP4 is because sort of maybe in some way the next interesting example after SL2, of course, although of course this is debatable, there's a couple of ways in which one could go. And it's also because I think later in this series, Kartik Prasanna will present some joint work with Harawa in which they study coherent cohomology of automorphic vector bundles on SP4. And I wanted us to get to think about SP4 a little bit. So without further ado, let's go. Well, there'll be a quick motivation and recap section. Then I'll talk, maybe the bulk of the talk will be about computing these cohomological representations of SP4. And then finally, I'll sort of say a few things about how cohomological representations maybe served as inspiration, or at least like serve as a nice way to introduce Arthur's conjectures. Okay, so for the first part, as I said, we're going to look at cohomological representations of SP4. These appear in the decomposition of the cohomology of arithmetic groups. So if gamma is a non-co-compact group, then we have to take L2 cohomology, which is the part that we can access by studying L2 of gamma mod G. But if gamma is co-compact, well, L2 of gamma mod G decomposes as a direct sum, as the completion of a direct sum of irreducible representations. And so in that case, the L2 cohomology is the whole cohomology. In that case, we're just studying, and it agrees with the classical Durand-Betty cohomology of the arithmetic group of group cohomology. Okay, so as I said, this bit of the cohomology decomposes over unitary representations pi h into the cohomology of each of these representations pi h twisted by our coefficient system E. And then there's multiplicities, which are sort of the automorphic input, the global input for the cohomology, which I will completely ignore, and it should say which I'll completely ignore. Okay, so after saying that, let me just remind you that the multiplicity of pi in L2 in the L2 disk of G mod gamma, so the part of L2 of G mod gamma that decomposes as a direct sum, as the completion of a direct sum of irreducibles. Okay, so last time, sort of at the end of the talk, we arrived at this conclusion that there's only finitely many cohomological pi for a given group and a given coefficient system. And today, what we're going to do is, in the case of the group SP4, we're going to look at these. We're going to look at these finitely many cohomological pi with non-vanishing cohomology. Okay, for simplicity of exposition, I'm going to assume that E is the trivial coefficient system. Doesn't change much about the arguments. There's a little bit fewer cohomological representations when E is non-trivial, or there can be, but in general, the arguments are very similar. And then really the big caveat that I want to say today is that the representations I'll discuss are not the Archimedean representations that appear in the Harawa-Prasanna paper. They work with coherent cohomology, automorphic vector bundles. That being said, I think that philosophically, I mean, the diagrams that will be in my talk look a lot like the diagrams that are in their paper. And I think sort of philosophically, to get us to think about SP4 and to get us to think about how these representations are sort of parametrized at the very least, it's not too bad of an introduction. But beware if you're trying to read that paper. It's not the same thing. Okay, so let's recall. Cohomological representation pi is determined by its k-types and the requirement that the Casimir eigenvalue of pi be the Casimir eigenvalue of rho, which in this case is the trivial representation. So it will just be infinitesimal character of rho applied to the Casimir. And then there's a complete parametrization of these representations in terms of these so-called theta stable parabolics of algebras, which allowed us to either sort of build up these Verma modules or to do a cohomological parabolic induction. We had sort of two ways to construct the cohomological representation. Okay, and so today what we're going to do is we're going to list the possible theta stable parabolics of algebras for G for SP4, and we'll say as much as we can about the corresponding representations. Okay, so some sort of a primer on SP4, just sort of the basics to situate ourselves. So the symmetric space associated to SP4 is a real six-dimensional manifold or symmetric space, the Siegel upper half space. So that means that if I have gamma and SP4, well, my quotient x gamma is still going to be a real six-dimensional manifold. So I'll have cohomology in a range of degrees between 0 and 6. But in fact, x gamma is going to have more structure. I mean, the symmetric space already has more structure. It's a complex variety. Yeah, some sense. Often it'll be a variety defined over a number field, but this is not what we're going to talk about today. So it's a complex variety, and so as such, the cohomology admits a Hodge decomposition, right? And so we'll see this image a lot during the talk, and we'll sort of fill it up bit by bit, but this is sort of the Hodge diamond of this variety x gamma. And then one last thing is that these representations, at the level of representations, they satisfy Poincare duality. And so whatever happens sort of below the middle of the diamond is going to be reflected above. Okay, with that in mind, let's get started. Okay, so as a little warm-up, let's just compute the cohomology of the trivial representation to sort of remember how this was done. Okay, so our coefficient system is just a trivial representation. And so a unitary representation that has the same Casimir eigenvalue as the trivial representation is the trivial representation. So that's completely valid representation for which we can compute the cohomology. From Tuesday, we saw that since the Casimir eigenvalue is the same on the trivial and the trivial, the ith cohomology of GK with coefficients in the trivial is just really the multiplicity, well, the space of k-homs of the ith exterior power of P. So P, right, was the sort of non-compact part of the Cartan decomposition of G, and so it's the same as the tangent space at the identity of the symmetric space carries a representation of K, and so computing so the cohomology can be identified with the space of k-homs between wedge I of P and C. So all we have to do to compute the cohomology with constant coefficients is just to compute the K invariance in wedge I of P. K, recall that K in this case is going to be the compact group, or the algebra of the compact group U2. And so the question is, which is a question that I asked last time during the talk if someone wanted to do a computation. What is the representation wedge I of P of U2 for I equal to 0, 1, 2, and 3? So I'm sure you all in the last 2 days did this computation. To give you the answer of what this computation is, I'll denote by nu of D the irreducible D-dimensional representation of SL2. Yeah, so nu2 has a center, so I'll sort of pull out the center at the level of the algebras, and then I'm left with the algebra that I could have called SU2, but I called SL2. just because. So I'm going to call nu D the irreducible d-dimensional representation of SL2, and then I have an action of the center, so I'll call chi t, where t is going to be an integer, the one-dimensional representation of the center, on which a fixed basis element, I didn't really want to write it, sort of, fixed basis element acts by it. So it corresponds to sort of e to the t I theta, sort of, if you think of it as the algebra of a circle. Okay, so given that, here is what the representations look like. So, okay, the trivial representation, that's easy. It's the trivial representation of SL2 tensored with the trivial representation of the center, the sort of 0th exterior power of P. Then P itself, one can compute, is reducible. So it's the three-dimensional representation of SL2, but sort of there's two copies of it. One of them is tensored with chi -2, and one is tensored with chi 2. Continuing, just computing exterior powers. The second exterior power is, again, if you decompose it into irreducible, has three copies of the three-dimensional irreducible weighted by different characters of the center, and then a copy of the five-dimensional and a copy of the trivial, weighted by the trivial character at the center. And then finally, third exterior power of P is this thing. So you have the trivial with a whole bunch of possible characters, and then V3 and V5 also with a whole bunch of possible characters. So this is a computation that you do in coordinates just by computing, computing wedge I of P. Okay, so what were we doing here? Oh yeah, we were trying for each wedge I of P to find whether the trivial representations appeared. Well, here's one place where it appears, is in, the 0th exterior power. And then it appears in a second place. Well, so to be trivial, it has to be trivial on both bits. So here's a second place where it appears, is in the second exterior power. And so we conclude that the cohomology of the GK cohomology of the representation C is one-dimensional if I is either 0 or 2, or, since I have Poincare duality, 4 or 6, and then otherwise it's trivial. So putting that in the Hodge diamond, here is what we get. If we want to look at the cohomology of the trivial, okay, and now I would need to argue that in fact it shows up in weight 0, 0, 1, 1, 2, 2, and 3, 3, sort of make this argument, but this is sort of where the cohomology of the trivial representation appears. In general, the cohomology of the trivial representation is often going to look like this for sort of other groups. If X gamma is a Shimura variety, it'll appear in every even degree. Also, it can be identified, I just wanted to say that, with the cohomology of the compact dual. So sort of to our symmetric space X, there's an associated compact dual symmetric space. There's a compact manifold which has a cohomology, and that's the cohomology of the trivial representation. In any case, it gives us sort of just a bunch of one-dimensional spaces in degrees 0 to 4, 6. Okay, so that was the trivial. Let's look at more representations. Let's remember a little bit how these representations were constructed. Vogel and Zuckerman told us that all cohomological representations are of the form AQ for Q, a theta stable parabolic subalgebra of SP4. We had this notion of a theta stable parabolic subalgebra. Let me remind you what that was. Right, we had this Cartan decomposition. Sorry, I'm denoting U2 differently than I did a couple slides ago. Sort of decomposing into the compact and then P. And then, okay, how did I make a theta stable parabolic? I took I fixed a Cartan in my maximal compact. Here T0 is the real Lie algebra corresponding to T. I take a point X and I times IT0, and then the parabolic Q is defined by, well, it has a Levy part, which is the sum of the 0 eigenspaces of at X, which is the centralizer of X, and then U is the sum of the positive eigenspaces of at X. So really what I did is I sort of computed at X for this element X. And that gave me this algebra Q. Okay, so let's see if we can use that definition to sort of compute. So here's the root system of SP4. I have this as before is 10-dimensional, I have this 2-dimensional torus, and then I have my 8 roots. There are 2 compact roots that are contained in the maximal compact K U2. So right now they're purple so that you really have them in mind. As I change the picture, they're just going to keep an arrow to remind you that they're there, but at some point they'll stop being purple. And then all the other roots, well, they're contained in P. And so what happens sort of is that sort of, and it reflects the fact that X gamma is a complex variety, is that I can give a decomposition of P, of this tangent space at the identity of the symmetric space, into a holomorphic and an anti-holomorphic part. So I can sort of give a complex structure to my Lie algebra. I didn't write it down, but I have sort of this decomposition into a holomorphic and an anti-holomorphic part, and how I'm going to draw it in my root system is that sort of what's sort of above and to the right of the compact roots is going to be P plus, and what's below and to the left of the compact roots is going to be P minus. Okay, and last thing is I'd rather work with weights than co-weights. So okay, I have X, which I can think of as a co-weight, and it pairs with the root. I sort of just sort of multiplication by this scalar that it applies on that root space. And what we're going to do is we'll just identify T with T dual via the standard inner product. And so that allows us to replace X by a weight instead, which I'll call lambda X, but quickly just lambda. So that really at X of G alpha will just be sort of lambda paired with alpha of G alpha. And so now also the inner product just looks like the standard dot product on R2. And so we'll just be able to look and figure out what's going on in terms of the signs of these inner products. Okay, and so now I've moved, the moral of this is I've moved from an element X in my Lie algebra to weight lambda. So the question will be, what types of weights give rise to what types of theta stable parabolics of algebra? Okay, so in summary, what we want to do is look at all the possible lambdas that will give us all possible Q lambdas such that, okay, Q decomposes as L plus U. So I'm going to try and do something. Okay, great. Q decomposes sort of as the direction of L and U, where L is the centralizer, so everything that dots to 0 with, and then U is the weights that are positively with my weight lambda. And okay, we're not interested in actual values here. We're only interested in sort of 0 or then positive. And so it follows that Q only depends on the sign of this pairing. So that's what we're going to do, is we're just going to vary lambda to get the signs of all pairings, to get all possible signs. And the final observation is that, well, I'm doing all this up to sort of SP4R conjugation. And if you think about it, what this means in terms of the picture, well, I want to conjugate this torus back into itself. So really, I want, it's sort of, I'm doing all this up to the action of the Weil group of the maximal compact, so Z mod 2Z. So in this picture, I'm only going to look at weights up to flipping the compact. Okay, so now that I've said all this, let's see what I can produce. Okay, so as I was saying, the theta stable subalgebra only depends on the sign of the pairings. And so let's look at the types of lambdas that can give me types of theta stable parabolics. The first possibility is that lambda is in the interior of a Weil chamber. This gives rise to 4 possible equivalent types. Equivalence class is what I'll call Borel type, because they look like a Borel subalgebras. In all 4 cases, the levy is just the torus. The dimension of U is 4. So in pink here, I have the 4 root spaces corresponding to U, and you can see it's really sort of the 4 root spaces that pair positively, that sort of point in the same direction as my weight lambda. And it's also the case, let's remember sort of from Tuesday's talk, that the lowest degree of cohomology in which we see this representation contributing, the associated representation contributing, is the dimension of U intersected with P. So in this case, it's 3. Right, so I have sort of, these are the roots contained in U, and then the 3 of them are contained in P, and 1 of them is compact. The only difference, so I'm going to show you these 4 equivalence classes of Borel type subalgebras. The only difference is going to be whether the intersection with P plus, the holomorphic part, or P minus, the anti-holomorphic. So let's look. So I have a first algebra that I'll call Q plus H. H stands for holomorphic, since all the non-compact part is holomorphic in this case. Then if I move lambda to sort of a different Weyl chamber, I get a different algebra called, which I'll call Q plus G for generic, Q minus G, and then Q minus H. So every time I've sort of put in pink the roots that are whose corresponding subspaces belong to U. The levy doesn't change, it's just the unipotent part that changes. And what changes really is the intersection with the holomorphic or anti-holomorphic part of the potential. Okay, so here we are, we have our 4 Borel type subalgebras. So this happened when we started with weight. Again, all that matters is the sign, not the actual values. So if I started with a weight that was inside of a Weyl chamber, in the interior of a Weyl chamber. Okay, there's a second possibility, which is that lambda could be sort of on the walls of one of the Weyl chambers, and this sort of gets broken up into 2 pieces. Lambda could be a multiple of the long root. So here I've drawn sort of such a possible lambda. It could be that lambda is here, and then we see that suddenly there are spaces that are literally perpendicular, root spaces that are perpendicular to lambda, and those are going to be in the levy, and then my sort of darker orange ones are going to be in the unipotent part. Okay, so I have here 2 possibilities up to the action of the Weyl group. One of them is I'll call QK plus, and the other one QK minus. K here stands for Klingen because it's that type of levy. And each of them satisfies that the dimension of U intersected with P. So if we look, the dimension of U, the orange ones, intersected with P, which is to say sort of anything off this diagonal, is equal to 2. So these will contribute to cohomology in degree 2 and 4. That's it. So okay, so from multiples of a long root, I get 2 possible theta stable parabolics. And then finally, lambda could be a multiple of a short root. And so up to conjugation, this gives rise to 3 possibilities. First, I have a pair. So let me show you sort of these 2. If lambda is a non-compact multiple, a multiple of a non-compact short root, then I'll get these 2 possible theta stable parabolics. Again, you see, for example, here in light blue, the roots that are part of the levy, and then in dark blue, the roots that are part, the unipotent, the root spaces that are part of unipotent. Okay, so these 2, they both satisfy that the levy is the full, the maximal compact, and then the dimension of U intersected with P is 3, so they'll contribute to cohomology in degree 3. We'll see this a little bit later. But we have a third one here, which is not equivalent to the other 2, which I'll call QM just because I needed a letter. And this one, it satisfies that the dimension of, so U intersected with P, so here and here, is equal to 2. Okay, so we've listed all possible theta stable parabolic subalgebras up to equivalence. So they came in 3 families. We had 4 of these Borel theta stable. We had 2 of these Klingen theta stables. And then we had 2 that came as a pair, and then a third one of these Siegel theta stables. And so to each of these representations, as we saw last time, Parthasarathi and Zuckerman, separately via 2 different techniques, but that arrived at the same solution, they attach a cohomological representation AQ. And now I want to see, okay, I have this finite number, 4 plus 2 plus 3, sounds like 9 representations. How do they contribute to cohomology? So which degree of cohomology do they contribute to? So let's start with this theta stable Borel, which give rise to discrete series representations. Yeah, something I haven't told you that's sort of part of the Vogel-Zuckerman machinery is that if the levy part is compact, then the representation is a discrete series. Okay, so I have these four representations, right? The holomorphic, anti-holomorphic ones, and then the two generic ones, plus or minus. And using Vogen-Zuckerman's calculation that we saw at the end of last time, namely that so this quantity, the amount of cohomology we're interested in, we can actually reduce it to computing just the invariance inside of a different, the K intersected with L invariance inside of a different representation for R, right? So it shifts the degree for R equal to the dimension of U intersected with P. Well, we saw in this case that R is equal to 3. And so for these representations, their cohomology is going to be concentrated in degree 3. So let's see the Hodge diamond. Then I'm going to sort of send each of these representations to the weight in cohomology, the weight, sort of the Hodge weights, to which it contributes a single dimension of cohomology. So I didn't sort of show that part of the computation, but each of these representations contributes 1 degree, has sort of 1-dimensional GK cohomology in degree 3. So the holomorphic goes here, the anti-holomorphic goes at the other end, and then the 2 generic representations sort of go to the appropriate weights. So now we have our 4 discrete series, and we've described where their cohomology sort of will contribute in the Hodge diamond of our putative symplectic Shimura variety. Okay, let's continue. We next had these 2 Klingon theta stable subalgebras giving rise. So when we do the constructions of the AQ, these give rise to 2 representation, pi k plus, pi k minus. In this case, this invariant R of pi is going to be equal to 2, so the representations will contribute to cohomology in degrees 2 and 4. And so one computes that pi k plus contributes H31, H02. Okay, I don't know why it flips. I don't control everything about these animations. And then pi k minus contributes sort of the reflected part in the Hodge diamond. Okay, great. So now we have, for 2 of our classes of cohomological representations, sort of described the degrees of cohomology and the weights to which it contributes. And finally, we have one last class of cohomological representations, these Siegel representations corresponding to these Siegel theta stables. Okay, I had these pi plus or minus s. And then I had this last one, pi m, right? I had sort of 2 that came as a pair and then a different one, pi m. In this case, it was interesting. It's a little different, right? The levies, in one case, the levy is compact, in the other case, the levy isn't. And so that'll affect sort of when you compute the dimensions of U intersected with P, so of sort of the quantity that dictates the degree of cohomology, you get different numbers. You get 3 for this one, and you get 2 for this one. So this one contributes to cohomology in degrees 2 and 4. This one contributes to cohomology in degree. These 2 contribute to cohomology in degree 3. And since, okay, I mean, so we'll have sort of, these representations won't contribute to cohomology in the same degree. That's fine. We'll start with M. Again, sorry for the flipping. So M will give us cohomology in degrees in weights 1, 1, and 2, 2. And then for these pi s, well, if you actually do the computation of the k-types that appear in the representation, we find that we've actually already described pi s. We sort of already know pi s. And it's, so pi s plus or minus is just a different construction of the same representation pi h plus or minus. So we're in a situation where different theta stable parabolic subalgebra give rise to isomorphic representation, which can happen. We never said that sort of different theta stables had to give rise to non-isomorphic representations. So we're in this situation, which is completely fine, in which there's actually redundancy. So sort of these pi s plus or minus, I'm not going to put them in this picture of the Hodge diamond because because we've seen them already. They're just under a different name. Okay. And finally, we have the trivial representation. There should be ones in weights 1, 1 and in weights 2, 2, but I decided to sort of not overload the picture completely. And that's it. We've listed all the cohomological representations of SP4 and where they contribute to cohomology. And one interesting observation that one can make is that there was no representations with cohomology in degree 1 or 5. And this is a specific instance of a pretty general theorem, which I found in the book of Burrell-Wallach, in which they also attribute to Zuckerman, which is that there's no L2 cohomology, there's no non-trivial representations with non-trivial cohomology in degrees below the rank of the group. So in this case, the rank of the symplectic group SP4 is 2, and so this tells us that there's no cohomology in rank in degree 1. And so there's only the trivial cohomology that always contributes in degree 0, but then there's no cohomology in degree 1. And so in general, the cohomology is going to be concentrated, sort of starting at the rank and going up to the corresponding degree above the middle. Okay. So what we've done so far is we've written down all cohomological representations of SP4 together with all their degrees of cohomology and all their Hodge weights. So here is the complete Hodge diamond, in which I've also sort of encoded the information that we produced the holomorphic and anti-holomorphic discrete series in 2 different ways from 2 different theta stable parabolic subalgebras. And so the rest of the talk, I'll talk a little bit about how one can use these cohomological representations to motivate some constructions in the Langlands program, and specifically related to Arthur's conjectures. I'm going to take a sip of water if someone has a question. Okay, so let me do, I know at least Saul Friedberg gave a very nice talk on the Langlands program in this series, and I feel like there's maybe been more since then. So I'm going to give a quick recap on the Langlands program, specifically on the reciprocity conjecture. Right, so according to the Langlands conjecture, there should be a correspondence, and here I'm putting a quote on the left, between Galois representations of a putative L group, Langlands group of Q, so some sort of extension of the Galois group by some other topological group. So these Galois representations should go if G is GLN to GLN, but if G is some other group to the L group. So that's the dual group of G with some Galois action. So that's the object, the Galois object, and it should correspond to automorphic representations, so irreducible summands of L2 of G of A mod GQ. And this should be witnessed. What is this correspondence? There's 2 infinite lists. You could just put them in bijection, but of course, 2 countable lists. But that's not what you want to do. You want to witness this by an equality of L functions. And then there should also be a local correspondence. So for each QV, so I'm giving the Q description, but of course this works for any number field. There should also be a local correspondence for each completion of Q, where Galois representations, here I've sort of removed the quotes because at least we know what the group is, right? This group, this Langlands group LQ, we don't really know what it should be yet. But locally we do know. And those should correspond to suitably nice, suitably nice, what does that mean? Smooth, unitary, anyways. Today it'll mean cohomological. Irreducible representations of the QV points of G. And here I've put V instead of P because, well, the place we're going to consider is not a finite place. We're going to consider the infinite place. And so what I want to talk about sort of for the rest is a bit about the local correspondence for cohomological representations. Okay. So as I said, we'll consider the case where QV is the real numbers, our group G is the group SP4, and suitably nice in this case will mean cohomological, or really, cohomological, unitary cohomological. Okay, so what's the group here? So L sub R, the sort of Langlands group of R, is just the vague group, which in this case is just sort of a group that has C cross as a group of index 2, and then the element, the quotient satisfies that J squared is equal to 1. Ooh! And then, sorry, there's a typo. It should read J, C, J inverse. So conjugation by J just applies the non-trivial unmorphism of C over R to C cross, just conjugates. Another way to think about this, which is maybe a little more sort of helps you wrap your head around, is that what we're looking at is it's the unique non-split extension of Gal-CR by C cross. So it has as a quotient the Galois group of C over R, which is of course just a fancy way of saying Z mod 2Z. And then as a sub has the multiplicative complex number, the invertible complex. Okay, and then what is the L group? So the L group of SP4 is SO5 or PSP4, because so SO5, but I'm going to use the exceptional isomorphism that SP4 is actually spin 5. So just so I have SP4 and sort of on both sides. So what I have is PSP4. I was thinking of this yesterday. What I really want is SP4. And I think it's because all the representations I'm considering have trivial central character. And so really, what I'm going to want my Galois representations to be, they're going to be parameters, and they're going to be maps from the vague group of R to SP4C. So that's the type of objects that I'm going to want to attach to my representations AQ that have trivial central character. Okay, so how do I do this? Here's a few important, well, a main important point is that if you've never seen this, it's tempting to want the Langlands correspondence to be a bijection. And unfortunately, it's not. So more than one representation AQ can correspond to the same parameter. And we'll call sort of the fiber above a parameter, the fiber above a Galois representations, the packet corresponding. So pi phi corresponding to the phi. Okay, so that will happen. And what we're going to do is, okay, so this is inspired by a beautiful expository article of Arthur called L2 cohomology and automorphic forms, in which he justifies, it's an article of probably the early 90s, in which he justifies his conjectures by sort of showing that at infinity, you can just see them happening in the cohomology of Shimura varieties. And I wanted to sort of present what I gathered from reading his article. And yeah, we'll sort of construct the packets so that natural endomorphisms happening in cohomology like give us for free the associated parameter, the associated Galois representation with here really a very simple Galois group or vague group. Okay, so what operators do we have naturally acting on cohomology? Well, or what groups? One can actually see the Hodge decomposition as the action of C cross, or really of restriction from C to R of GM. And so the sort of action of C cross is that on the HPQ piece, the complex number Z will act by Z to the PZ bar to the Q. Sort of one can view the Hodge decomposition like this. This is what sort of appears in the definition of Shimura varieties, for example. Okay, so for the purpose of this and following Arthur, we'll work instead with a twisted action, so that on each HPQ, Z acts not by Z to the P Z bar to the Q, but by Z over Z bar to the Q minus P over 2. So this is to make things consistent, sort of the global picture in the local places at other places. It also has the convenient feature that the action only depends on the difference between Q and P. So for example, the action on H20 will be the same as the action on H31, and the action on, I don't know, H02 will be the same as the action on H13. And so this will sort of give us scalar actions on the with the same eigenvalue on the columns of the Hodge-Diamond. Okay, and of course, C cross is not the full group WR. It has index 2. And if I induce the representation on HPQ up to the full figure group, I just get sort of an induced representation, a two-dimensional induced representation, which when I restrict back to C cross gives me the action on HPQ plus the action on HQP. So what we should think really is sort of that the mirror pieces are together a two-dimensional representation of WR. And then, well, I guess in the middle, we'll get actions with trivial action of this element J. Okay, so that's one operator on the cohomology. Second one is that there's a Lefschetz SL2 action that appears from cupping with the Kähler class. So if I sort of think of the Lie algebra of SL2, I can think of my raising operator acting by raising, by sort of, increasing the degree of cohomology by sort of 1, 1 in each of the 2 degrees. And then I have a lowering operator, and then sort of there's a corresponding eigenvalue of the diagonal element, which I'm calling J because I've already used H quite a few times too. Okay, and so this gives me sort of an action on SL2. I mean, there's this, give me an action of SL2, which let me integrate it to an action of the group SL2. And a good thing is that because of our choice of normalization of the action of C cross, these actions of WR and SL2, they commute, right? So as I sort of act by SL2, I remain in the same eigenspace for WR. And so what I have is on this whole Hodge diamond, I have, I break it up into two-dimensional representations of the big group like this. And also representations of SL2. Okay, and so this suggests, if you're Arthur, right, I'm not saying sort of to us, but that instead of associating our representations to our representations a parameter, the big group R to SP4, we could instead associate to a representation what are called Arthur parameters from the product of WR and SL2 into SP4. And the idea is going to be, so what are these going to be? Well, SP4, then if I send it into GL4, I get a 4-dimensional representation. And what I'm going to want to do is I'm going to want this 4-dimensional representation that comes from the parameter to be the same as this natural action of WR times SL2 on the cohomology that I just described. So from sort of the Hodge decomposition and from the Lefschetz SL2. Okay, so what we're going to do is we're going to group these representations into packets, and these packets are going to be associated to parameters in these parameters, and we're going to have this agreement between the two. So this is an instance of the local part of Arthur's conjectures. I mean, this is sort of the most basic statement that one can make, I think, of the local parts of Arthur's conjecture, which have been proved now. It's called the endoscopic classification of representations. So it's proved in several cases for quasi-split symplectic and orthogonal group by Arthur, then for quasi-split unitary groups by Mach, and for general unitary groups by Kelly, Menges, Shin, and White. So sort of by now what I'm telling you is a theorem. But when we're reading this article of Arthur, it's still a conjecture. And in particular, these packets that I'm talking about, they were constructed early on in this whole story by Adams and Johnson. Okay, so let us consider our representations that we've constructed, and we'll see how their cohomology can fit nicely into packets that correspond to these four-dimensional representations of WR times SL2. Yeah, let's start with the trivial representation. Well, that's pretty easy. We'll just take the trivial representation of WR and then the four-dimensional representation of SL2. I'll give you a map. They'll give us a map into SP4. So the trivial on the face side, and then the four-dimensional representation of SL2. And okay, it's already four-dimensional. We'll associate that to sort of to a packet containing only one element, namely the trivial representation. Okay, the next natural four-dimensional representation is the one corresponding to the four discrete series. In that case, yeah, so although it's not obvious here because this is not an irreducible representation, it's the sum of two reducible representations, right? Some global considerations, like the reason why this representation is reducible is just because WR is too small of a group. But if it was sort of the WQP for any QP, it would be sufficiently big. So yeah, global considerations indicate that they should share the same L packet, and that this should correspond to an irreducible Galois representation. Okay, and so here we have it. What do I have? I have the trivial representation of SL2, right? There's no raising and lowering operators here. Everything happens on the same column. But then on the Galois side, I have the just appropriate induced representation where I induce this bit plus this bit to the whole representation of WR. Okay, next, I had my pair of Klingon representations that contribute to H2 and H4. Okay, and here they fit very nicely into a four-dimensional representation. I have sort of a two-dimensional representation of SL2 that raises and lowers, and then I have a two-dimensional representation of WR that flips the two. And so in this case, what I have is really the tensor product of two irreducible two-dimensional representations of these two groups. And that will just correspond to the packet. Sorry, this should be a K. Obviously, when I prepared these slides, at some point I got very confused between Siegel and Klingon, but it should be a K here. So this packet containing these two representations corresponds to this tensor product of two irreducible representations. Okay, so these representations are non-tempered representations, but they're also non-trivial representations. So that gives us a non-tempered A packet. And as I said, they each contribute 2-dimension of cohomology. So that gives us total a 4-dimensional representation, which is what we want. Okay, and finally, we have just the middle, the last representation, pi m. And pi m has cohomology, a 2-dimensional sort of cohomology, GK cohomology in degrees 2 and 4, but that's not enough because our parameters should be 4-dimensional representations. And so we have to put something else in this packet. And so what we decide to add to this packet, when I say we, I mean Adams and Johnson, Arthur, etc., are the two discrete series that came from the same type of theta stable Lie algebra as pi m. So remember when we were doing this stuff with the theta stable Lie algebra, we had sort of an isomorphism between representations that we had already constructed, but that were isomorphic to new ones. Well, we're now going to put them all in the same packet together. And so this will give us, so this packet of representation contains pi plus or minus h and pi m. Sorry, this should be pi m. It's here. And it corresponds to a parameter that's reducible. So here we have a 2-dimensional representation of SL2. It's here. And then a trivial representation of SL2 together with a 2-dimensional representation of the big group. So here and here. Okay, so in this case, the representation is really sort of the direct sum of two representations, the blue one and the pink one, if you will. And so this is a feature of local Arthur packets, that they are not disjoint. And so that's one thing I wanted to illustrate with this example, is that so what does Arthur's conjecture do? The local Arthur's conjecture, it sort of that's it. It constructs packets of representations corresponding to parameters, but these local packets, they may not be disjoint. On the other hand, they'll get glued together into global packets corresponding to automorphic representations, which in this case, no, I want to be careful. Yeah, will be destroyed. And so in Arthur's own words, sort of his conjectures are really a tool to study the global automorphic spectrum. Okay, so in summary, what have we done today? So we've constructed 4 A packets of cohomological representations associated to our 4 A parameters. So the packet, which I'll call pi G, containing only the trivial representation. The packet pi B for Borel, containing our 4 discrete series representation. The packet, which I call psi K for Klingon, containing our 2 Klingon representations, so sort of the one that looked like this. And then this slightly more bizarre packet, containing this last representation pi M, and then having intersection with the pink one, because they both contain the holomorphic and anti-holomorphic discrete series. For each packet, again, sort of we knew how to make them, or we knew what the parameter was supposed to be, more importantly, because we could just read it off the action of natural operators on the corresponding piece of cohomology. And I'll just observe, because this is a pleasant feature of the situation, that each packet corresponds to a conjugacy class, sort of an SP4 conjugacy class of theta-stable parabolics of algebras. So the theta-stable parabolics of algebras, for example, giving rise to all the representations here, well, they're not SP4R conjugates, since they're distinct, but they're SP4C conjugates. So sort of the whole conjugacy class gives us all these representations in the packet. And when one constructs the parameters a little bit more rigorously, this appears in the construction. And here, for example, the fact that 2 different theta-stable parabolics gave rise to the same representation is sort of encoded in the intersection of A packets. So sort of these theta-stable parabolics, which felt maybe a little artificial, they also actually tell us something about A parameters, so about where these representations fit sort of in a Langlands type classification. Okay, finally, I've told a very sort of nice and easy, or not easy, but sort of a toy picture story of this. But Arthur's conjecture, in fact, says much more and predicts much more. It doesn't just give you the sort of partition of the representations into packets. There's an action there's a commuting action of a third group, S psi, so a component group of a centralizer of the parameter. And in this way, each representation gives rise to a representation of this small two group S psi. And this induces, anyways, Arthur's conjecture also demands that some specific trace identities should be satisfied, having to do with the commuting action of this third group S psi. So there's a sort of third, more complicated bit that is part of the conjecture, that is part of what Adams and Johnson's proved when they constructed these packets, which I'm completely slipping under the rug and not talking about. But I don't want to sort of make you believe that the story is over at this point. And then finally, we saw that some of the parameters, they sort of factor through subgroups of SP4, so we to the L group of SP4. So we saw it here because we had a reducible, in this blue packet, we had a reducible A parameter that sort of split into 2 bits. So you can imagine factoring through subgroup of SP4. And for this orange parameter, well, it sort of factored through the tensor product of 2 two-dimensional representations. And so this suggests that the parameters actually sort of come from parameters on smaller groups, and that the representations should be related to representations of smaller groups. And this, I think Professor Kim also talked about, sort of this should be an instance of, this is an instance of functoriality, so of different groups. It should be witnessed by trace identities among the packets, and this should be, and this is an instance of functoriality, this identity between packets. Okay, I hope I have convinced you that the representation theory ad infinity of cohomological representations of SP4 is both completely tractable, but also rich enough that we can see sort of a whole bunch of phenomena happening. So non-tempered A packets intersecting, possible functorial lifts. And yeah, that's why I want to talk about SP4 today. Thank you very much.
Thank you, Mathilde. That was a very nice talk. Are there any questions?
Yeah, I mean, what are other such groups for which such a discussion is already available or done, like SP4?
Pardon me?
I mean, what are other such groups for which the discussion of this type is already done in detail?
Oh, it's all classical groups, and I think maybe all reductive Lie groups. So I have to say, like, a wonderful resource here is this article of Nair and Prasad, in which they sort of give a lot of details about packets of cohomological representations. I know that if you want a super explicit description, I think, yeah, it's somewhere in the literature for any family of classical groups. And maybe people who work on exceptional groups can sort of add to that. I'm sure it's known for G2 or something like that.
Yeah, okay.
Any other questions?
So, could I ask a question, Mathilde? Sorry, can I be heard?
Yes.
Yes.
So just going back to the thing. So, for example, the 4 discrete series for SP4, you have to put them in a packet because for global reasons, you know somehow that the corresponding Galois representation should be irreducible. But for the other packets, is there a convincing reason that, for example,
I think the only one for which there is for the trivial, we're good.
Okay.
I think for the and I think for the orange one, if I can sort of go back to the orange one. Shoot. Did I stop sharing? Oh no,
I think so.
Sorry. Give me 5 seconds. Okay. What's going on? Sorry. I don't know what's going on. Okay, I don't know why it closes, sorry. But for the one, for the 2 non-tempered representation, I think one can make a convincing case that it is an irreducible representation. It's a tensor product of an irreducible representation of SL2 with an irreducible representation of the Fay group. So that gives you a natural 4-dimensional irreducible representation.
Okay.
I think
the other one,
so the sort of Cytokurka one is sort of the more interesting one. I would say, one should ask Adams and Johnson, but I think it's the representations that make the trace identities work out, right? When they're constructing these packets, they're not just, what they want is stability, right? And if you have pi m on its own, it's not stable. And so you have to add the characters of other representations in sort of to get stability. And these are the right discrete series to add in to get stability. They do give this whole thing that really, I didn't say it very precisely, but take this class of theta stable parabolic subalgebra. gives you a class of a conjugacy class of levies. You take the dual. I mean, I think I read this in your paper. I'm not sure if I'm explaining your paper. But right, then you use representations into this dual levy to create the parameter.
Right. But there's sort of not a like irreducibility of the global Galois representation is pretty convincing thing, right? So
yeah.
Whereas,
but in this case, global Galois rep.
No, I mean it can't be since it's in different degrees.
Yeah,
right?
Exactly.
But somehow maybe perhaps the thing, maybe that is maybe if you look at the isotype of cohomology, but then you look at it mod P or something, they all appear in one sort of
I mean
indecomposable but not irreducible sort of module of dimension 4 or something. Okay, this must be well studied thing. So
right.
I'm not.
I
don't know. Yeah.
It's beyond my.
Yeah. Okay. Yeah. Somehow I think. Yeah. Okay. Great. Thanks. Yeah. Very nice talk. It was kind of interesting. Yeah. So.
Any other questions? Comments? Okay, thank you, Mathilde.
Thank you.
Sorry, Mathilde.
It's okay. All good.